what I'm going to talk about today is generalized convolutions. So Maria asked me to do a Blackboard talk. I think she wanted to avoid me showing holiday pictures, but I'm talking about convolutions. And let's start with convolutions. And convolution is a standard thing in digital signal processing. So I will work entirely discrete, and essentially f and g are two multivariate functions defined on the integers. So it's simply everything will be discrete. There will be a little bit of polynomials and Laurent polynomials in it, but mainly everything will be totally discrete. And the standard operation, you could replace that by the complex numbers. That's not really a big deal. Let's keep it real for the moment. This is not so relevant at that point. The convolution is the standard operation in digital signal processing. Oops. So the convolution is defined as f star g, which is taking a sum, this infinite sum, and this is f of alpha, g of the argument minus alpha, and you sum over everything. So a convolution is just something, but you could say it's a product on these discrete objects. There is actually convolution algebra and everything. Let's look at this in a slightly different way. So what happens here is, in fact, I take the function g and I shift it by t to the minus alpha. Still, very simple observation. So I take this function and I shift it by, I write this as a shift operator, but then I can take a different point of view because it's actually independent. G is a function and I apply this thing to g. And if you look at this, what this is actually a polynomial in the difference operator. So I can write this as, say, f, usually I use the flat now, f flat of tau, and this is the C transform of f. So f flat is a formal polynomial in, more precisely, a Laurent polynomial in C. Now, the main thing is, this of course only works if f is finitely supported. Otherwise, you're working on nasty things like infinitely supported formal power series. You can do things there, but it's getting significantly more difficult, or nasty, or unpleasant. So let's take a slightly different point of view. Let's consider the convolution as a bilinear form. So let's say f times g, it's an obvious bilinear form. So it maps sequences. I use this little L notation. It makes sequences to times sequence to sequences. So it's not a bilinear form in the sense that it gives you a number, but it's a bilinear function, it's a bilinear operation on that space. Okay, big deal. We can make a slightly different perspective here because there's another way of writing it. So it's also the C transform of tau applied to, sorry, it's the C transform of f, of course, applied to g. So we could say, in order to make this well defined, the point of view could be, let's make one of these two guys, maybe the f, the signal processing people will say that's the filter. Let's make it finitely supported. That's what people like anyway. So let's make the filter finitely supported, but we could take a different point of view and say, we consider this as an operation that takes as one argument a Laurent polynomial, and that takes as the other argument a sequence, and generates a sequence. Sorry, what's the difference? The difference is if we see what happens here if we apply the difference operator. Because if we apply the difference operator to g, any difference operator to g, then this is just the same as multiplying f by the monomial. And now things start to make sense, because on this side here we have sequence spaces, and we may talk about shifts of sequence spaces, shifts of sequences. And here we have Laurent polynomials, and we will talk about multiplication with monomials, which is a standard operation within polynomials, and a standard operation within Laurent polynomials. Let's have slightly more fun. I mean, all these things, say this f of tau. Now let's take this just as a polynomial, or let's call it a polynomial p of tau applied to g. This is what people call a difference equation. That's a difference equation. And now we are in several variables, and usually a single equation is not enough when you go to several variables. So you could think about systems of difference equations, like taking a set capital F. Take finitely many Laurent polynomials, and these finitely many Laurent polynomials, they define you a system of partial difference equations. It's the same thing like differential equations, just work with difference equation, and now I have a system of difference equations. So easy way to go. Now comes the next very simple observation. So let's look for homogeneous solutions. Let's look for homogeneous solutions of the system of difference equations, because that's what we're essentially looking for. And then we make a very interesting observation that actually, if we shift the zero function, we get the zero function again. I mean, that's probably suitable for that time of the day. So if we shift the zero function, we get the zero function again. And this means, this is, by all our definitions, the shift of f star g, which is in fact just the shift applied to g, or it is at the same time the set f multiplied with the monomial applied to g. And as trivial as this is, this gives us some insight. Because it tells us that, in fact, the homogeneous solutions, G here, they form a shift invariant space. Because that's what we see here. If G satisfies the system of equations, then tau alpha G satisfies the system of equations as we trivially shift around the zero function. Of course, the solutions form a linear space. So observation 1 is, I'm not going to write this as a theorem. Observation 1 is, if we take the kernel in this respect, so we give a system of difference equation, we take the kernel of that, this is shift invariant. Now, what does shift invariant mean? Shift invariant means that if I take the space, call it G, and apply the shift operator, I get my G again. For any shift operator, for any alpha. But there's a second observation. This is, if I fix a set of solutions, if I fix a set of solutions, and I look for the difference equations that annihilate it, in fact, now this is a subset of Laurent polynomials. Oh, it means that I can multiply with arbitrary monomials. Again, it's a linear space. So in other words, this is a Laurent ideal. Which means that we can now play a very nice algebraic duality. So on the side of the solutions, we talk about shift invariant spaces of sequences. And on the side of the filters, we talk about ideals of filters. There we make use of the algebra. There we go to the world of Laurent polynomials. And it's very important that we work with Laurent polynomials here. So there's a lot of overlap between this talk and Bernard's, for those who were there, which is no accident. We're talking about the same thing. So the result should be the same in the end. But there are some subtle differences in the point of view, which I find actually quite interesting and quite good, because it's always a nice thing to look at the same thing from different perspectives. Because that, as a person who works in photogrammetry now, is what gives you a chance to give a full three-dimensional reconstruction of the object in the very end, if you look at it from sufficiently many perspectives. Good. So we have an ideal on the one hand side, and we have a shift invariant space on the other side. So of course, if you talk about shift invariant spaces what's the easiest way to get a shift invariant space? I mean, everybody knows that. That's the standard trick that you could call completion. So you just take all f in your set capital F, you take all shifts, and you take the span of that. That's the shift invariant space generated by some set. And of course, one of the nice questions is when are these shift invariant spaces finite dimensional and all that stuff. And this has been considered not only in the B-spline context, in a lot of contexts here. So that's the question that we're going to make. What are some simple observations? If I take a shift invariant space that's generated by a compactly supported sequence, what's its dimension? It's infinity, because you just can shift the function around the compactly supported one so that the supports of the shifts don't intersect. These are finitely many linear independent elements of the shift invariant space. So the finitely supported are not the interesting ones. What is a way to get a finitely supported space? The simplest way to get a finitely supported space is again another, as a good friend of mine, Jan Schü, would say, semi-trivial computation. So what you do is you just look what happens if you take an exponential sequence. So theta to the alpha. Theta, all components being non-zero. So whenever I will talk about thetas later, it will always mean that all the components are non-zero. And that's the beauty of Laurent ideals. And that's one of these wonderful subtleties that occur in the proofs, because since we are working with not just with integer, but not just with non-negative integers, but with multi-integer shifts, it turns out that whenever we will have common zeros of objects later in the Laurent ideal, we automatically have these entries non-zero. So we have to care for that when we work on the details, but we don't have to care for that here. So now apply this, the shift operator to that guy, which is just that plus alpha, and incredibly but true, it's theta to the alpha times the function. So in other words, the exponentials are eigenfunctions of the shift operator. If you take an exponential, the respective shift invariant space has dimension 1. Are there other shift invariant spaces of dimension 1? The answer is, of course, no. And we will see that all finitely supported, all finite dimensional shift invariant spaces of sequences are, in fact, exponential polynomial spaces. So the way is extremely simple to get there, because suppose G is a finite dimensional shift invariant space. Now we take this duality. We start with our G, and then we know, wait a second, the set of annihilators for this finitely dimensional shift invariant space is an ideal. So in other words, there exists an ideal I, or let's write it in terms of a basis. So that's the ideal generated, Laurent ideal generated by a finite set F, such that F is exactly the kernel of this bilinear thing when putting in G. And it takes a little bit of effort, but not so much. And then you show that, Bernard would call that Artinian, that the dimension of all Laurent polynomials modulo that ideal equals the dimension of the shift invariant space, say, generated by a finite set. So the dimension remains the same. Which means if this is finite dimensional, then in fact the respective Laurent ideal has only finitely many common zeros. So we have a system of Laurent polynomials, a Laurent polynomial system of equations that can be, with a little bit of care, be turned into a system of equations. You just have to avoid some sort of spurious zeros. It has finitely many zeros. And that would be easy if all the zeros were simple. If all the zeros were simple, these finitely many zeros would give you exactly the exponentials that span that thing. 90% of the fun that comes here is occurring when you look for the multiplicities. Which brings you to the interesting question, what is the multiplicity of common zeros of an ideal? Is multiplicity still a counting element? And the answer is no, if you want to do it in perfect subtlety. And this result is actually due to Gröbner in 1937, when he developed a multiplicity theory for common zeros of polynomials. And funny enough, in his paper, he was characterizing the homogeneous solutions of partial differential operators with constant coefficients. And he was characterizing them as, surprise, surprise, exponential polynomials. And several of the tricks that you also see, for example, in least interpolation and so on, have really been used and developed by Gröbner in this extremely wonderful paper. I mean, the only disadvantage, fortunately not for me, once in my life I'm lucky, the only disadvantage is the paper is in German. But it's an excellent paper and solves this multiplicity question. Multiplicity is not an issue of counting. I run around with this for at least 10 years now. So what's a simple zero of a multivariate function? You would say it's 0 there. What's a double zero? Okay, it's 0 there and some directional derivative is vanishing. But what's a triple zero? It could be two first-order directional derivatives, linearly independent, or it could be a first-order derivative and a second-order derivative. Both is a valid notion of a triple zero, triple common zero of a set of functions. And the real thing for multiplicity at a zero, say theta, it is in fact a space q theta of polynomials with a nice property that q theta is de-invariant. Which means whenever a polynomial is in that space, its derivative is in the space. Any derivative of the polynomial is in that space. This is actually the same as being, it's a recurrent theme. It's exactly the same as being shift invariant. So whether you say this thing is differentiation invariant or shift invariant, it's the same. And Gröbner's theorem, and this is 1937, one of the consequences of that theory he develops, I would say, says when I is a finite dimensional ideal, then this is true if and only if I is the kernel of q theta of d applied to some polynomial. So it's instead of all polynomials, q theta of d, and then followed by an evaluation at theta. So it's finitely many zeros with multiplicity. And it's the perfect analogy to the univariate case. That's the multiplicity, and that allows us to distinguish between different forms of multiplicities of triple, quadruple, and so on zeros. And the number of these number of zeros counted with multiplicity, which means the number of zeros, the sum of the dimension of these spaces is exactly the codimension of the ideal. So that's the business we have, and that's how we can write things for differential operators. It's getting slightly different for difference operators because the multiplicities, yeah? When I have only one zero? Sorry. Of course, then the union over all thetas. Yeah. So, or let's write it this. It's more than one zero, of course. Each theta is a zero. So you take all the zeros, you take all the multiplicity spaces, and it's exactly the kernel of this thing. Thanks. Okay, so this is that sort of thing, and now you can do this for difference operators. And if you do this for difference operators, it's almost the same. So let's try to look like a theorem once, at least once. So what I need is, I have a finite set of Laurent polynomials, and I want this ideal to be zero-dimensional which means that the solution space of the difference equation is finite dimensional. Infinite dimensional is a little bit more ugly. Then the kernel of this, which means exactly the set of homogeneous solutions of the difference of the operator is. Now, again, we take all common zeros of this ideal. It's just a matter of the ideal. Which way you define the equations doesn't matter. It always just depends on the ideal, not on the equations. So you take all common zeros of the ideal, and then you take the kernel, and it's not q theta. You have to apply a certain strange operator to it, and you have to rescale the polynomials, and then you apply the point evaluation. The difference between different, lot of differ now, the difference between difference and differential operators is that for the difference operators, you have to make a modification. You have to make a slight modification. And this, by the way, is Pruning. This is Pruning's problem, because you start given an f. This f is an exponential sequence. And what you want to do in Pruning's problem is you want to find the proper annihilating filter. And this is, in terms of signal processing, exactly what Pruning did. So you do the opposite way. Now I said I start with a different. I mean, that's actually surprisingly, it's a style how many people work. I mean, they take an exponential sequence, they have a solution, and now they look for a problem for which this is a solution. And this is exactly what happens in Pruning's problem. You look for the difference equation that has this, or the system of difference equations, that has this sequence space as solutions. So that's, in fact, what you do in Pruning. We will get to that in a second. But there is another thing. I still have to tell you what this operator L is. And for this operator L, we do two funny things. There are two nice ways of writing identities on polynomials. One way is to use the Taylor expansion. The Taylor formula is writing this thing as an identity on polynomials. And another identity on polynomials is you take 1 over alpha factorial. Now you take the alpha difference operator, and then you would take what's called a Pochhammer symbol here. Don't worry if you don't know, this is a Newton interpolation formula. So one is Taylor, one is Newton, which is good because they were contemporary anyway. And now we just switch things. We just switch the functionals. And we call this operator L. And then, of course, they are not the same, but in fact, the other one is the L to the minus 1. And these are two operators that map polynomials to polynomials, preserve the degree, map d-invariant spaces to d-invariant spaces, and this is exactly the action that happens here. You looked for a name for this operator for a long time, so now my favorite name is Stirling operator, because in fact what happens with this operator is that the action of L just means take the coefficients of f and apply the Stirling numbers of the second kind as a multiplier to these coefficients. That's exactly what this operator does. So this is this little bit of mystical number theory that occurs there. And this shows that it's no surprise that in all these subdivision things, Stirling numbers pop up all the time, because in many of these polynomial reproduction stuff, you are trying to mix in some way differentiation and differences. So that's also what happens, what connects standard difference operator, standard derivative operators to the so-called theta operator. Theta operator is another cool thing. It's like you take a partial derivative with respect to a variable, and then you multiply the variable again. The cool thing is it has all the monomials as eigenfunctions. So that's a very nice and simple difference operator. Okay, now let's get back to Pruning's problem, because what we're going to do in Pruning's problem is exactly trying to find for a given sequence, and we know that the sequence is a exponential polynomial sequence. We take this exponential polynomial sequence and we try to find the respective annihilating filter or the respective annihilating system of filters. I mean, we look for the difference equation or the system of difference equations. And how we are doing this, we are using linear algebra, because once it gets down to computations, it usually gets down to linear algebra. And in order to do linear algebra, we start setting up, and now it's, again, oops, alphabets up. It's again getting up to setting matrices, and you can either set up a Hankel matrix, which is you evaluate f at alpha plus beta. Alpha runs over a set capital alpha, so keep in mind this is not an A, this is a capital alpha, and beta runs over a set capital beta. And you build these matrices, and then what you try to do is you try to find the kernel of these matrices. Because the kernel of this matrix, since this matrix represents, oh my god, this is a correlation, so maybe, since I always talk about convolutions all the time, I can of course also do it for convolution. I can of course also do it for convolutions with a Toeplitz operator, which doesn't matter. And I can look at these things and can look at the kernel. Since they just represent the convolution or the correlation, it is exactly finding the dual filters. So finding the dual filters are hidden in the kernels there. And now, of course, it boils down to doing linear algebra, and this matrix gives you enough information about the dual filter. Okay, now I should say, actually I should say what Pruning is doing, even if people said that. So the issue is reconstruct a function, which is now f of x, which is some coefficients f, say theta, and then theta to the power of x. So I dropped the exponentials here. I can't drop e here. I wrote it in the plane theta to the x way. These are complex numbers. The interesting thing, these are supposed to be unequal to 0. This is the exponential thingy, and if you want it as exponential polynomials, then you are allowing for polynomial factors here. And the polynomial factors are, again, what comes with a multiplicity. So you want to reconstruct such a function from the samples. The samples are here, the samples of your function, and all you've got to do is to look for the kernel. You just have to take these matrices. For example, you start with a set A, and then you can build it you can build it block by block, you can column by column, you can build it by column blocks, and this is the heart of all the Pruning solution algorithms. You may look at Esprit, you may look at music, you may look at SMILE, which is a multivariate technique based on Grübner basis, and then there is a sparse harmonic interpolation technique that still has no acronym yet. But there are still lots of possibilities of solving that problem, and you can really do it numerically with one side condition. The space P alpha, which is the span of the monomials, sorry, let's put it this way, which is the span of the monomials contained in alpha, must be an interpolation space. Interpolation space for the thetas. And if there are multiplicities for thetas with multiplicities. And now it's getting interesting. Because usually the only information you have is, everything is getting interesting here, this is why I like it. The only information you usually have is, say, it's at most 10 frequencies. So there are at most 10 entries in the sparse representation. Now in the univariate case, you would say, what is an interpolation space for 10 points? Hey, great, take the polynomials of degree 9. This is what always gives you these small matrices in the standard case. Now what is an interpolation space for, say, 10 points in the multivariate case? Because all of a sudden geometry matters, and you don't know anything about the geometry of points. So the simplest thing would be you look at the space pi cardinality of theta minus 1. So this is the number of counted with multiplicity. This is the number of frequencies that you have. You look at that space. If you want to do it a little bit more clever, you can take the whole square, which of course is in the interpolation space because the triangle is contained in the square. And But you may ask the question, what is the smallest interpolation space? So this is a really interesting algebraic question. So what is the smallest, with respect to dimension, the least dimensional polynomial space that allows you to interpolate at n points in an arbitrary number of variables? To my knowledge, there is practically no answer to that. And this is a really ugly problem, especially once you start to think about it. But we can make if we can make our life easier and request more, because we need a space that consists of polynomials. So what's the smallest space of polynomials that allows for interpolation, spanned by monomials that allows for interpolation at points? I still don't know it. But if I want the interpolation process to be degree reducing, so it just should have the capability, if I give it a polynomial of degree 5, the interpolant has to be of degree 5 again, then there exists a unique minimal solution, which is here inside the simplex, which is the hyperbolic cross. That we heard about. So this is, as far as I know, the smallest universal interpolation space but with the extra assumptions of degree reducing and monomials. Okay. So this is how we get to Pruning's problem, and to some extent, this is what brought me here. I mean, that is what got me interested in all these problems, because you can now talk about these operators HAB. You can talk about Hankel operators, say, of a certain rank. If alpha and beta are finite, then these matrices have a rank. This HAB, I should say, of F. It's nicer. And then you can take the supremum over all AB and say this is the rank of the Hankel operator. You can do the same thing with the Toeplitz operator, the rank of the Hankel, the rank of the Toeplitz operator for such a sequence F. And suppose it's finite. What is the rank? No surprise. It's exactly the dimension of the shift invariant space. And in some way, this is exactly the mathematics behind Esprit. Because Esprit is one of these Pruning algorithms that work a lot with shift invariant spaces, that work a lot with shifting around things and with shifts. And since the dimension of the shift invariant space agrees with the dimension or with the rank of the Hankel operator, it doesn't matter which way you do things. The algorithms are theoretically equivalent, but everybody knows that famous Yogi Berra statement. In theory, there's no difference between theory and practice. In practice, there is, and then it's about the numerical implementations. Yeah, so again, you take the Hankel operator. The Hankel operator has a kernel. The kernel, the infinite one, the kernel has an ideal structure, exactly gives an ideal structure, finite zero-dimensional ideal, common zeros, and so on. This is how you solve that thing. I mean, you build these matrices, you build the ideals, and it's really possible this way with numerical algebra to do something like 200 frequencies in 13 variables. And actually, you can do it on a laptop in less than 2 minutes, which corresponds to solving some, I think, 3,000 quadratic equations in 13 variables. But with numerical computer algebra, you can do this quite fast. So in the end, it's just a little bit of QR and some eigenvalue computations. This is where then the companion matrices and multiplication tables and everything enters. But I promised to say something about generalized convolutions. So what's the generalization in that stuff? What are we going to generalize? So it's like with a student who did not pass the exam so far because he did not generalize things. Let's go to the first blackboard. And I always have difficulties, I must say, in writing the correlation. Because usually the correlation between F and G is this strange star, which I never managed to write on the blackboard. So keep in mind the correlation is some F alpha G plus alpha. It's not commutative anymore, but that's not the problem at the moment. I don't like that. And then I had this stupendous insight that actually plus alpha is minus the identity times alpha. So in fact, it's a correlation with a matrix in there. So let's put a matrix, psi, into our correlation, and let's just multiply with psi alpha here. And all of a sudden, of course, we have our favorite subdivision operators and whatsoever, and it of course fits the same terminology. It's the C transform of tau to the psi. What you see immediately is that in this type of generalized convolutions, unimodular matrices play a special role. What I want is only one requirement on psi. Psi is supposed to be an S by S integer matrix, and its determinant should be non-zero. I'm not saying anything about expanding. Expanding would be subdivision operators. I'm just saying plug in an arbitrary psi here, and the difference equation that we now get is something like the C transform of tau to the psi applied to G is equal to 0. And now we can, of course, ask ourselves the questions, how do the homogeneous solutions of this look like? Which are the kernels of subdivisions, which are usually also these stability losses in the filter banks, for example. So if the subdivision operator, which is a low-pass reconstruction part of a filter bank, has this type of defect, has a homogeneous solution, then you are in trouble. I mean, these are the instability things. People know these are exponential polynomials, but how do we find them again? So what happens here? It needs a little bit more of terminology. And, okay, here's the terminology. So we've seen that before. I think it was in Vladimir's talk yesterday. So the first thing is, of course, the obvious decomposition into subgrids. So we take psi times c to the s, we take these psi's, and the psi's are just, you take the half open unit cube, multiply it with psi, and intersect it with the integers. You don't even have to be expanding here. It's no problem. I mean, this is the immediate consequence of the Smith factorization. So you don't have to do anything spectacular here. You just use the Smith factorization of the matrix psi. Smith factorization means that you write psi as, I just have to find some unused letters. Say x dy. These are diagonal matrix, and x and y are unimodular matrices. Smith factorization is beautiful. Actually, I found out that Smith has his birthday on the same day as I have, so I like it even more. And I should remember that yesterday was the 146th anniversary of the death of Hankel. So in this respect, my talk is one day late. Otherwise, I could even, it doesn't matter. But it was not the talk that killed Hankel. I'm innocent. Okay, anyway, so it's just the Smith factorization. These two guys are unimodular, and this is Gauss elimination with total pivoting and division with remainder. The beautiful proof in Marcus and Mintz is one of the must-reads. So it's a beautiful thing. And we do this decomposition. Now, once we've done the decomposition, now it's getting a little bit more notation, so I better take this piece of paper with me. Once we do this, we can look at subsymbols. And here I did the C transform with the minus alpha. Now I took to do the symbol with the plus alpha. These are two different things, but the difference is very minor. In fact, it's the same thing as subdivision people usually struggle with forward and backwards difference operators. And depending on whether you use symbols or C transforms, one fits in naturally, the other one needs a little bit of effort. Anyway, so the subsymbol, and that's what's known to every subdivision person, is you take the subsequence, psi plus psi alpha, so we reduce to one of these components, one of these decomposition components of the C to the S, and then you multiply it, say, by C to the alpha, and since the C transform is always a little bit flat, the symbol gets sharpened. So the F sharp is the symbol. And then there is one more thing that's funny. These are, and everybody knows them. These are these famous numbers. If you see it for the first time, you think, well, did they drink too much or did they have too much champagne? But in fact, there's a point about that. It's this e to the 2 pi I. You can put a minus there if you want. It doesn't affect it at all. And then there is psi to the minus transpose. So the inverse of the transpose multiplied by eta and eta. So this set here is what I call e psi, and eta is just in the dual, in the transposes. Now this looks like strange numbers, but once you get used to the calculus of taking a matrix power of a vector, you in fact find out that these numbers have a very nice property, and that's, in my opinion, what really defines them. And it is that C eta, that should wake up the last one, C eta to the psi is 1, 1, 1. Which means, and that's the good sign, they are signs. They're not omens, they're signs. They're xith roots of unity. I mean, the second roots of unity in one variable is plus and minus 1. All plus and minus 1 combination are exactly the roots of unity with respect to the matrix 2i, the most famous subdivision matrix. So whatever you see there is it's a sign. Just a slightly more complicated sign, but I mean, the moment you get to, but that's nice, the moment you get to theory of functions, signs become complex. It's getting more complex. You cannot avoid it. Okay, so this allows us to talk about a symmetric zero. A symmetric zero of a polynomial is just a point, say zeta, such that it vanishes at all sign variations of the zero. So this is just C eta first component times first component of that one. So just a component-wise product. No big deal. And now we can talk about the homogeneous solutions of this type of difference equations. And the theorem says, let's just say annihilator of some exponential sequence. And there are two possibilities. So if and only if. The first one is the total symbol. The total symbol has a symmetric zero. This is nice, because if you just talk about a zero of a single multivariate function, multivariate functions, when they just except they are non-zero constants, have a lot of zeros. They have a whole lower dimensional variety of zeros. Turning this into a symmetric zero all of a sudden forces the ideal to be finite dimensional. Now, how do you compute this symmetric zero? It's not like taking a polynomial with a large lower dimensional variety, and now you go walk over all the variety and check if something is symmetric there. That may take a while. But there is an equivalent description, and that says that zeta to the psi is a common zero of the subsymbols. So the subsymbols are these guys here. Sorry, I forgot the psi here. The subsymbols are these guys. So now you have finitely many polynomials, or Laurent polynomials. This is an ideal that's hopefully zero-dimensional. If it's not zero-dimensional, you're in real trouble, because then your generalized convolution annihilates a lot of things. But you just look at them, and then the xith power of that magic zero you're looking for is contained in there. There are a few more funny aspects. So for example, you can also consider the Hankel submatrices, like things like that. So you do subsampling in one of the dimensions. This would be the Hankel operators related to the subparts. And then what's very easy to see is actually the rank is independent of the xi, so they don't really care for the xi if you make A and B large enough. So that's not a problem. The rank of these h xi's coincides with the rank of h, if and only if we have this symmetric solution, symmetric zero situation. There is an opposite thing, and then the rank of h is much, it's the sum of these ranks, so it's cardinality, a determinant of the matrix times the rank. In the case, in the case when the zeros are in a certain distributed in an asymmetric way. So the point is, whatever you do with these subdivision and whatsoever operators algebraically, it has to do with symmetric zeros now. Last thing, what happens about preservation, polynomial generation, these famous things by subdivision operators, let's just say by generalized convolutions to keep it simple. It's the same thing, but for generation, we have to give up one of the zeros. We have to give up the zero at the origin. So polynomials are the exponential zero. So theta is equal to 0 for polynomials. So we look at a rotation of that, and we take all symmetric zeros except the one that corresponds to eta equals 0. If you normalize there properly, we get reproduction of polynomials. So that was the story I wanted to tell about these things that have been interesting to me in the last years. Even if you didn't like the talk, I liked it. So who cares anyway? Thanks for your attention. Thanks for still being here. Thank you very much. Can I use 1 second for a short announcement of my own? Next February, I'm running, several people here in the audience know that, some don't know it yet. I'm running again a small workshop in a remote place in the Bavarian forest in Bernried. So it's tough to get there. We help you there. It's even tougher to get away from there. But you're rewarded with a nice 3-star superior resort hotel with a large swimming pool, and you're punished by talks. So the price is something like 100 euros per night with large rooms, conference, soft drinks at the conference included, 3 meals, and now I'm getting overrun. So whoever is interested and has never heard about it, please send me an email. The important thing of this conference is it's not the place to show your importance by coming 2 days later and leaving 3 days earlier and saying, I spent -1 day at the conference, so please reimburse me some conference fee. So we expect people who want to come there to come on Sunday evening, arrive on Sunday, leave on Friday. But usually the reward is really a nice week with nice colleagues. Okay, you have to stand me, but otherwise with nice colleagues and interesting talks. So it's just whoever thinks he has something nice and interesting to share, you're welcome. Send me an email because we'll send out the announcements in some of the next weeks. Sorry, and now questions.
Thank you, Thomas, and for a very nice talk. I enjoyed it. So any questions for Thomas? Oh.
that was your applause.
Many years ago, Charlie Micheli and I, we wrote papers, I think in an American journal of mathematics, or American Mathematical Society, about the solution of systems of difference equations that came or were motivated by box splines. Mm-hmm. So these were systems involving directional differences. So very close to maybe what you are thinking of in terms of subdivision schemes. There was a complete, concrete characterization of kernels and whatever, in particular in connection with what people call zonotopes. I wonder, is that in any way related? You just don't know the paper.
It must be because, well, I don't know the details. I think it really has to be dug out. But the sonotopes are related, I think, what's it called? These Newton polytopes that are, for example, covered in the second volume of the book by Cox, Little, or She. Probably Bernard knows more.
This is explained.
And there are ideal theoretic methods.
Characterization, and you get all these exact representations like exponential polynomials.
Yeah. So what's most interesting to me, and what was most of the work in there, is this relationship between the precise multiplicity space of the polynomials, of the common zeros, and the exponential, the polynomial space that's attached to one of these exponentials. Yes. So that was the part that interested me most, and I did this way. But I have to look up that paper again. I'm aware of that, but so far I was driven there by Pruning. Maybe I have to look at the B-splines again now. The box splines again.
Box splines.
Box splines. Yeah, B is dangerous. I agree. Multivariate B.
Any more questions?
You have some results known when you consider difference equation with non-constant coefficient or differential equation?
This is just the difference equations framework is with constant coefficients, because the coefficients have to be turned into a Laurent polynomial, and then you would probably have to consider Laurent polynomial. Well, if the coefficients come from a ring, then you could consider Laurent polynomials over that ring, but that's not the type of world I would feel at home immediately. So maybe if there's some simple rings, it could be possible, but I don't know.
Okay, so we have no more hands up for questions. So let's give Thomas two rounds of applause, seeing as I missed the first lot.